Okay, so we're now starting chapter 5 on open mappings and their applications. And we begin by looking at open mappings and the open mapping lemma. Now, the main theorem about open mappings is the open mapping theorem, which says that if you've got a surjective continuous linear map between Banach spaces, then it's automatically an open mapping, which means that the image of every open set is open. Now, you don't normally expect a continuous map to take open sets to open sets. Typically, they don't. If you have a constant continuous maps don't usually take open sets to open sets. But if you add in the condition that it's a surjective continuous linear map between Banach spaces, then you get the fact that it maps open sets to open sets for free. And in particular, if it's also bijective, that tells you that the inverse is automatically continuous, which is a striking result. There are various things like this in the literature about automatic continuity of inverse maps when you know the map is continuous. In the general setting, you know that's not likely to be true. There are plenty of continuous functions with discontinuous inverses around, but there are certain other examples of this sort of phenomenon, such as if you've got a map from a compact space to a Hausdorff space, which is continuous and bijective, then its inverse is automatically continuous as well. So there are a few other examples of this in the literature. So an open mapping then, and there are actually some slight differences in the literature in this, but this is what an open mapping means officially for a map from X to Y, and more generally for topological spaces, is that the image of every open set, so if U is open, T of U should be open in the image. Now, because we're working with norm spaces and linear maps, the image is going to be the image is also going to be a linear subspace if you take U to be the whole of X. So notice that T of X must be open in particular, because X is open is X. But T of X is a linear subspace, and it's not empty because it's got 0 in it. Non-empty, open, linear subspace. A linear subspace with non-empty interior has to be the whole thing. So it has to be surjective in this setting. And that's where there's a slight difference in the literature. One can ask whether the linear map is open regarded as a map to its image. So that's the alternative. If you don't want to force it to be surjective, then you could ask, is it open where it could be as a linear map from X to T of X? So that's a different question. Where you put the subspace topology here, or the obviously restricting the norm. In that case, you can ask the question about even non-surjective maps, because obviously everything is surjective to its image, and so you can ask separately whether you're an open map to your image. Yes?
So you say that it is surjective, we use the fact that a subspace has interior, a subspace of a bigger space has
Yeah.
interior, empty interior, has to have an empty interior. It's like
A proper subspace must have empty interior. So if you've got a proper linear subspace of a non-space must have empty interior. So you have non-empty interior, then you must be the whole thing, if you're a linear subspace. So T of X is a linear subspace and then the interior in Y of T of X non-empty implies T of X equals Y. Okay, so next we get a familiar type of exercise. Very like the continuous is the same as bounded, or equivalent norms are uniformly equivalent. What does it mean to be open? It's very like the continuous implies bounded, except that somehow something is the wrong way around. So you're an open mapping if and only if there's some positive constant. So that this time, for every y in the image, you can find an x in the domain which is not too big, and so that T of X equals Y. So this is like boundedness in reverse. It's not surprising, because if this was a bijection, this would be exactly the same as saying the inverse is a continuous map. So a linear homeomorphism from X to Y is a linear isomorphism continuous in both directions. So notice T to the minus 1 is continuous if and only if T is open. Once T is bijective. If T is bijective, T to the minus 1 is continuous if and only if T is an open mapping. And T to the minus 1 is an open mapping if and only if T is continuous. Because one is about images of open sets and the other is about pre-images of open sets. So they go in opposite directions. Okay, so there's your conditions of being an open mapping. And now, I want to bring in a major tool when dealing with open mappings. And it's, this is, if you like, the open map, the hard part of the open mapping theorem uses the bare category theorem. But there is another bit of the open mapping theorem which doesn't use the bare category theorem, and this is it. And not everyone extracts it separately. Some people prove this in the middle of proving the open mapping theorem, but because it's an important result of its own and it's got lots of applications, we're going to pull it out separately and call it the open mapping lemma. Not everyone calls it that, so it's not a standard name in the literature. Some people call it the open mapping lemma, others don't call it that, and other people just include it in the middle of hidden in the middle of the proof of the open mapping theorem. So here is the open mapping lemma. It essentially says if in an appropriate way you're almost surjective and you're almost an open mapping, then in fact you are surjective and you are an open mapping, and a bit more. So here there are some constants in this statement. So you've got a continuous linear map from X to Y. X has to be Banach. Y doesn't have to be Banach. Y can just be normed. Though it will turn out that if the conditions of the lemma are satisfied, then Y has to be complete as a consequence. Then there are these two constants M. M could be any positive constant, and it plays roughly the role of the element in the domain not being too much bigger in norm than the thing you're trying to get to. So this constant M for the moment is playing the role of the element of the codomain you need shouldn't have to be too much bigger than the element that you're trying to get at, which is what you needed for the open mapping theorem. But there's another constant alpha as well, which should be strictly less than 1. And in fact, from below you'll see that naught is less than or equal to alpha is less than 1. But that's automatic from the conditions that are coming up in a minute. This is a number less than 1. The idea is that you're going to try to approximate things in the domain whose norm is less than or equal to 1 to within estimate alpha. So you must have alpha less than 1. If alpha was 1, then of course you could approximate things in the codomain. If you have something in the codomain whose norm is at most 1, then of course you can get within at most 1 of it by using the element 0. This would not be acceptable. Okay? So I don't want to allow 0 as my estimate. I need to find some other element in my codomain whose norm is not too big, at most capital M, and so that the image of it is within alpha of y, and alpha is strictly less than 1. So alpha equals 1 would be no good. But this alpha is constant here, less than 1. So so it's not that each element you can get it's not just that you can get strictly less than 1 away from everything. It's that there's this good bound less than 1, and you can get within that bound of everything in y in the closed unit ball using elements in X whose norm is at most M. So the idea is that you've got these relatively crude approximation to start with. Alpha could be 0.9, so you haven't managed to get very close yet. But the idea is that first you'll get within alpha, and then you will estimate the error. And since the error will only have size alpha, your next estimate will get you to within alpha squared. Then your error will only have size alpha squared, and your next estimate will get you within alpha cubed. And you will have a succession of better estimates. And because of the way things work, we'll be able to add up all those estimating things and get something that hits the right vector exactly. So that's what's going on behind the proof. Now that bit about alpha plus alpha squared plus alpha cubed is where this m over 1 minus alpha comes from. So although originally you only needed things norm m to get close to things with norm 1, if you want to hit it, that was to get within alpha. If you want to hit it exactly, then you end up with m over 1 minus alpha. Notice that alpha was strictly less than 1, so that's still good news. Once we've done that, we've shown the thing is surjective, but we've also shown it's an open mapping because, remember, you need to have some constant capital K, and that will be our capital K. The constant capital K you need for the definition of open mapping. And so once you've got that, of course you get that T is surjective and it's an open mapping, and then rather nice extra surprise at the end, that forces Y to be complete. You can't do this unless Y is already complete. So let's prove this. I've already told you roughly the structure of the proof. Let me get a copy of that in front of me so that I don't change notation in the middle. So we'll set y1 equals y. I'm going to do something else first. First note, sorry, where are we at the moment? I'm on the wrong proposition. 5.3, right? Sorry about that. Under the conditions of 5.3, using the usual scaling, you know about scaling up and down by your norm and so on. For all y in y, there is an x in x. Since y no longer has norm less than or equal to 1, we're going to have to scale by the norm of y. So the norm of x will now be, at most, that same constant m times the norm of y. But that's because you might have to scale by a factor norm y to get yourself down to the ball. And again, you don't expect to get within alpha. That gets scaled by norm y as well. And such that norm of tx minus y is small or equal to alpha norm y. So all we did was scale everything by norm y. And we'll use this frequently. So we can use that again and again. So we set y1 equals y. And you choose x1 in x with norm x1, we're using star of course, norm x1 less than or equal to m times norm y1 equals m norm y, such that norm tx1 minus y, y1 is more equal to alpha norm y1 equals alpha norm y. Okay. Let's subtract off our first estimate. You set y2 equals y1 minus tx1. So that's roughly alpha times as big or less. And now we take x2 so that tx2 estimates that. Using star, you choose x2 in x with norm x2 at most m norm y2, and such that norm tx2 minus y2 is smaller or equal to alpha norm y2, which of course is equal to alpha times norm y1 minus tx1, which is less than or equal to, if you look here, that's less than or equal to alpha squared times norm y1. So it looks like we're doing better. You set y3 equals y2 minus tx2, which is equal to y1 minus tx1 plus tx2 in brackets, which is y1 minus t of x1 plus x2. And you proceed in this way. Continue in this way, and what do we get? To obtain sequences xn in x, yn in y, with what do we achieve? Ym plus 1 is equal to yn minus t of x1 plus xn. Norm xn is at most capital M times norm yn. and norm yn plus 1 is more equal to alpha to the n times norm y1, which is alpha to the n times the original norm y. This yn wasn't right. That's just y. Y is the same as y1. Let's rewrite that. That's y1 minus the first lot. That's y minus t of x1 plus up to xn. And perhaps if I put one more in, it's equal to yn, of course, minus txn. So this is what you achieve this way. Let's have a look at what we've managed here. So this one shows you that yn plus 1 is the error when you use the sum of the first few x's to try to get t of it to be y. So notice yn plus 1 is the error when using t of x1 plus up to plus xn to estimate y. And this error is getting very small geometrically because alpha is less than 1. So it is getting very small. But also, norm xn is not too big either. Norm xn is at most m times norm yn, which is less than root to alpha to the n minus 1 times norm y. So in fact, you can sum the norms of the xn's. It's a geometric series, at most, and it's finite. And now there's a result on the question sheet that tells you that if the sum of the norms converges, then the series itself converges in the Banach space. So since X is a Banach space, since X is a Banach space, the series sum from n equals 1 to infinity of xn converges in X, or in other words, the limit as m tends to infinity of the sum from n equals 1 to m of xn exists. That's what that means. So we set x equal the limit m tends to infinity of this series, which is just what we mean by that infinite series. Then we can estimate the norm of x. Is at most the sum from n equals 1 to infinity of the norm of xn, which is, got the estimates about there, that's less than or equal to, I lost an m somewhere, didn't I? If I look back at the top there, I should have had m times the norm of yn, so it should have been m in there. Norm of ym was at most alpha to the m minus 1 times norm y. So now we've got that right. We can put that in here. That's at most the sum from n equals 1 to infinity of m alpha to the m minus 1 norm y, which is exactly m over 1 minus alpha times norm y, just adding the geometric progression. If you sum alpha to the m minus 1 from 1 to infinity, you get 1 over 1 minus alpha. And finally, I want to show, for this bit of the proof, we need to show that Tx equals y. Since T is continuous, Tx is equal to the limit as n tends to infinity of, we'll have an m, limit as m tends to infinity of t of the sum and that should be xn, going up n equals 1 to m, which is equals the limit as m tends to infinity of sum from n equals 1 to m of t xn, but we already know that that's y, because that's y. Let's just go back up for the moment and have a look at what these things do. If you look at what y minus t of the first things is, it's ym minus txn. That's actually ym plus 1, whose norm we know is rather small. So since this distance, the norm of this remember that the norm of this is norm yn plus 1, which tends to 0. So that tells you that as n tends to infinity, t of x1 plus whatever up to xn is tending to y. So t is onto, and you can get at y using something whose norm is at most m over 1 minus alpha times norm of y. And we've done the hard work. Now, so that proves 1. Two follows immediately, as observed earlier. And so that leaves us with 3 to prove that y is complete. But I'm going to use that series criterion for completeness again. We just have to check that if you've got a series in y which is sort of absolutely convergent, if you put the norm signs in, then it must converge genuinely in y. So let yn be a sequence in y. We show that if the sum of the norms converges, so if the sum of the norms is finite, then the series converges. And this is equivalent to checking completeness for norm spaces by the exercise, by a question on the question sheet. This condition is equivalent to completeness. And it's easier to check than looking at Cauchy sequences. So this is quite a common way to prove, yes?
If we had an isometry between the two spaces,
Yes.
that is, in this case, we really have to learn that y is something.
Surjective isometry.
Yes.
If you have a surjective isometry, then you just use the metric space result, that if two metric spaces are isometric, one is complete even only if the other is.
So can we do something like this, saying that t is surjective, and then we have, in one, we have that norm axis norm.
There's no work. That's exactly what we're going to use, that you can get without, we'll use this constant capital K equals m over 1 minus alpha. And we'll use that to pull things back. But unfortunately, you can't just do that any old how, because if you use a Cauchy, if you try and do it, it's not quite as easy as the usual thing. If you just pull back a Cauchy sequence like this to some appropriate elements, it may not work for the differences between the elements of the Cauchy sequences. There is a problem there. If you have a look at this and try and work directly with Cauchy sequences, you'll find that there's a slight obstacle. If you can make it work, that would be interesting. But usually there's a slight problem if you go directly to Cauchy sequences. I'll show you how this proof works, and you can try to imitate it working with Cauchy sequences. But because it's there exists x rather than there's a unique x with such and such a criterion, there's a problem. The flexibility in the choice of x's gets you into trouble. If it was a bijection, then it all works fine again, and you get Lipschitz continuity in both directions, and you're fine. Does that make sense? It's something to think about. You can have I mean, it's a good thing to look at. It's a good idea. Okay, so given that the series converges of norms is finite, choose, and somewhere we should set, I should say, set K to be this thing. Let me set capital K to be m over 1 minus alpha to save myself some writing. Here, let's put that down there. So we'll choose xn in X with norm xn no more than capital K times the norm of yn, and with txn equals yn. Okay, we can do that. We just pull them back individually. Then the sum of the norms of the xn's are okay. That's less than or equal to sum from n equals 1 to infinity of capital K times the norm of the yn is finite. So the series sum of xn converges in X. Because X is a Banach space. But then, again, by the continuity of T, limit as m tends to infinity of the sum from n equals 1 to infinity of yn equals the limit as m tends to infinity, we need an m again, I keep doing that. That's the limit as m tends to infinity of the sum from n equals 1 to infinity of t xn. Why does it keep coming at infinity when I'm on m? T xn, yn is t xn. That's the limit as m tends to infinity of t of sum from n equals 1 to m of xn equals t of sum from n equals 1 to infinity of xn. Okay, so strictly speaking, one investigates this limit. You look at what's going on here. As m tends to infinity, the partial sums tend to the full sum. T is continuous, so limit of the t of the partial sums tends to t of the full sum. And that tells you the other limits all exist. So that, in other words, sum from n equals 1 to infinity of yn exists and equals t of sum from n equals 1 to infinity of xn. So y is complete. So y is the Banach space. Okay. Any questions about the proof of the open mapping lemma? Okay, next time we'll talk about some of the implications of the open mapping lemma for quotient spaces. We'll talk a bit about Uerson's lemma and Tietze's extension theorem. And then we'll move on to actually doing the proper open mapping theorem. Okay? So we'll stop there for today.